Generate and test is a very easy concept to understand in the field of artificial intelligence. You have a problem out there with a large number of possible solutions, possible in the sense that only a very few of them are actually solutions to the problem, perhaps even only one, while the rest are unsatisfactory in some way. The great majority of these possible solutions are nothing more than a waste of time and computing resources to calculate. As well as being a means of attacking problems in artificial intelligence, the approach is often used in related fields, such as experimental psychology, although in those other fields it is often referred to simply as trial and error. Ideally, a computer program would immediately come up with a true solution to the problem, the needle in the haystack that represents the best possible option. However, without knowing in advance what that is, all too often the computer has to come up with all the possible solutions, from which it can select the best one. This is generate and test. Investigate every single line of attack for the problem and take the best solution that you can calculate. What you can see here is generate and test outlined as a flowchart, or algorithm if you prefer. If all you want to do is find some solution to the problem at hand, and you don't care whether it's the best solution or not, this simple approach is fine. Just crash through the solutions available, and as soon as you find one that works, stop. You might attack the problem like this if time were pressing, or resources for implementing that solution are abundant, one of those money no object situations. For many problems, simply finding a solution won't do. It has to be the best solution. These are called optimization problems, and they require much more work, as you can't just stop once you've found a solution. Instead, you have to keep going, and if a better solution turns up, you replace the one you've already got with the new solution. An example should make this clearer. The classical problem of the travelling salesman. Here's a map of 5 cities, each linked by roads to all the others. In the problem, we assume that there is only one road between any given pair of cities. The table on the right gives the distance between each pair of cities in miles. The salesman must start in any one of the cities and visit each city once and once only, and in doing so, minimize the number of miles travelled. Some versions of the problem insist that the salesman must end up in the same city in which he started. This is clearly an example of the second type of generate and test problem, where the solution must be optimized. If any solution were good enough, then we would simply start in one city and follow roads between them in any order. After all, there's a road between every pair of cities. The generate and test approach to this problem is simple. Pick a city to start and calculate the distance to all the other cities. Then for each of those other cities, add the distance to all the other cities without backtracking to the original starting point, and carrying on in the same manner. Essentially, we are calculating all possible routes, one of which will be the shortest one. That's the answer to the problem. Yeah, it's a brute force approach. For this 5-city problem, whichever city you start in, there are 4 possibilities for the next one. For each of those 4 possibilities, there are 3 possibilities after that, without backtracking to the starting point, and so on. The maths gives 4 times 3 times 2 times 1 possibility, i.e. 24 candidates to try. Mathematicians amongst you will recognize this as the factorial function. The computer works all the possibilities out, then picks the one that gives the shortest distance. 24 routes aren't many to calculate, but what if there had been 50 cities, or 500? 5 cities gives 4 times 3 times 2 times 1 possibilities, 24. 6 cities gives 5 times 4 times 3 times 2 times 1 possibilities, equals 120. 10 cities gives 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 possibility, which is more than 3.5 million. As the number of cities increases, even only slightly, the number of combinations that need to be tested explodes exponentially. The travelling salesman problem is what we would call a non-polynomial question, which essentially means that the question of using a generate and test strategy quickly becomes impossible to implement for anything other than the simplest of situations. In general, problems involving crashing through all the different arrangements of items are placed into one of 2 groups. The polynomial or P-class problems are those in which the number of possibilities generally increase with the number of items considered, cities in the case of the travelling salesman, raised to some power. For instance, if there are n items, the number of possibilities might be n squared, or n cubed, or even some polynomial that you get by adding these. If the number of possibilities were, say, 10n to the 4th plus 3n, that would be a polynomial class, P-class problem. As n increases, the calculations become harder, but are still manageable. Many problems, however, including the travelling salesman, are what we call non-polynomial or NP class. In this case, as n increases, the number of calculations shoots up way beyond any simple power of n, or any string of those powers added together. We've seen that for the travelling salesman problem, the number of possible routes is equal to the factorial of n. Other problems give the number of possibilities that might be 2 to the power of n, or 10 to the power of n. For any appreciable value of n, these numbers become ridiculously large. For instance, let's compare the polynomial function n to the power of 4 with the function 4 to the power of n. With n equal to 10, n to the power of 4 gives you 10,000. Large, but doable. 4 to the power of 10, on the other hand, gives you 1,048,576. Yikes. That's probably the reason that generate and test isn't the first technique we would reach for when trying to solve problems. To be fair, though, there are ways in which it can be streamlined. Consider this situation. I have to get from my house in the north to Diane's house in the south, visiting all my friends once and once only. It's a travelling salesman all over again. There are many possible routes, but there's only one path across the river, and that's via the bridge. Clearly this problem divides neatly into 2 parts, finding the best route north of the river and finding the best route south of the river. The best overall route is just these 2 routes joined onto each other. However, this divide and conquer approach can also be applied at a finer level. For instance, there are several possible routes from Ian's house to Bob's, but only one best route. Once calculated, this can be stored and used along with all the other best routes between houses to calculate the optimum. This ability to retain partial solutions can reduce the workload considerably. There are some places when the generate and test approach is perfectly reasonable, but many more where it is either simply inefficient or impossible to apply. Let's compare an example in maths with another one in logic. In 1637, the French mathematician Pierre de Fermat scribbled what was to become known as Fermat's last theorem in the margin of a copy of a book he was reading called Arithmetica. Tantalizingly, he claimed that he had a proof for the theorem, but that it was too lengthy to fit into the margin, thereby driving mathematicians to the edge of insanity ever since. The theorem goes as follows. Consider the equation on the screen. 3 numbers, a, b, and c, which might all be different, or 2 of them might be the same, are all raised to the same power n, and lo and behold, it is found that by adding a to the power of n and b to the power of n, it gives you c to the power of n. What Fermat's last theorem states is that there are no integer, i.e. whole number, values of a, b, and c bigger than 0 that work in the equation if n is also an integer value bigger than 2. For instance, if n is 3, then there are no integer values of a, b, and c that will make that equation true, or if n is 4 or 5 or anything bigger. For centuries now, mathematicians have been trying to prove it, and until the last decade of the 20th century, all they could do was crash through immense quantities of numbers, showing that Fermat's last theorem did indeed appear to be true. There's your generate and test, if you like. Try all the possibilities and look for any that prove the theorem wrong. Out of all those billions of figures tried, if the mathematicians had found a single combination of a, b, and c and n that worked, the theorem would be wrong. But we simply can't prove the theorem this way. However many numbers are tried, there are always more out there, and there's always a chance that the very next number, just beyond the point where we decided to stop, is the special one that invalidates Fermat's last theorem. In 1993, Andrew Wiles finally succeeded in proving the theorem mathematically, putting a whole generation of mathematicians out of their misery. Now contrast that with this statement from logical inference. The letters stand for logical values, which can only be either true or false, or 1 and 0 if you prefer. Exactly how the logic works doesn't really matter here. Suffice it to say that given that a, b, and c can only take one of 2 values each, then there are exactly 8 possible combinations of those values. If you work out both the left side and the right side of that equation for each of those 8 combinations, you find that they match precisely. This lets us state categorically that the statement is proven. With a limited number of values to test, generate and test has made a watertight deduction. So there you are. In the right situation, generate and test can be a powerful technique. If there is a solution out there amongst all those different permutations, then generate and test is guaranteed to find it. The downside is that the workload on the computer can be very, very large enough to make it impractical. Generate and test works best in conjunction with various techniques to make it more efficient. Next week, I shall introduce you to one of those techniques, heuristics. That's the end of the lecture. As usual, please do comment below, and also don't forget to click the like button and subscribe to the channel if you haven't done so already. Thank you.